All right, let's go on to the second part. This is the second video. This will actually be a lot shorter, I hope. We've already done questions 1 through 5. Now we're going to deal with questions 6 through 11. And 6 through 11, not as hard as you think, but a little bit complicated. So make sure you kind of pay attention. It deals with this picture right here. And what we have is the sun is shining on the earth. This right here, 0 degrees latitude, is the equator. This would be 30 degrees north latitude. Seattle would be about right here. 60 degrees north latitude. And the North Pole would be 90 degrees latitude. Notice that the sun hits directly above the equator in this scenario right here, versus the North Pole where the sun is hitting at a very low angle. So once again, if we're looking at, we're using my flashlight here to determine how bright it is. This is what the sun intensity is like at the equator. At the North Pole, the sun intensity is about like this. Look at that. It's a lot more brighter at the equator than it would be at the North Pole. So that's what we're actually kind of working with, is this intensity. And understand, the more intense that the sun is, the warmer the temperature is going to be. So let's take a look at question number 6. Number 6 says, with a metric ruler, that means, in other words, use the metric system, the little small dots on the ruler. Measure the total width from point X to point Y. Now, once again, this is kind of hard to do, trying to do this onto the screen. So what you're going to need to do is, on this piece of paper right here, you're going to measure straight up. You're just going to measure how far it is in centimeters from point Y to point X. And so I'm measuring about 5.8. So I would write 5.8 centimeters. It asks you what that is in millimeters. That would be like saying 10, 20, 30, 40, 50, and then 8. So that would be like 58 millimeters. Now don't follow my numbers because I might have a different copy. I think I'm going to try to make that picture bigger for you guys so you can see it a little better. But 5.8 centimeters, for me, that's how far it is. That's the total amount of radiation hitting the earth coming from the sun. So that would be 100%. Okay? So to answer question number 6, you're just telling me, what did you measure with your ruler? To go on to question number 7, it says, assume the total width of the incoming rays from point X to point Y is 100%. That's what we just talked about, intercepted by the earth. Each centimeter would equal how many percent? Each millimeter would be how many percent? So what I'm trying to say here is that, what would 1 centimeter be if that was 100%? All right. So there's 5.8. That's your total. To figure out your, you can bring out a calculator here. To figure out the total amount of percentage for 1 centimeter, if 5.8 is 100%, so you would type in the calculator 5.8 oops, did something wrong here. Okay, so sorry, I didn't have my calculator up on the screen. Let me show you guys my calculator. So I would take 100% and I would divide that by 5.8. That's how many centimeters are in there. That means every 17% would represent every centimeter. So that would be 17%. Is 1 centimeter. And a millimeter would be 1/10 of that. So that would be 1.7% for every centimeter. Okay? Which brings us off to question number 9. Use the protractor. say that again. Oh, so what they want, I'm sorry, I skipped one. Question number 8. From 0 to 30 degrees, how many millimeters is that? And what percentage is that? So now I'm going to go back to this picture right here, and I'm going to go from 0 degrees to 30 degrees, and I'm going to see how many millimeters that is. So that would be about 2.9 millimeters. And I'm sorry, not 2.9. That would be 29 millimeters. 2.9 centimeters, 29 millimeters, and I'm going to multiply that times 1.7 to see what percentage that is. So once again, I'm going to bring up my calculator again. .29 millimeters multiplied by, oops, let me show you guys my calculator on screen. So 29 millimeters multiplied by 1.7, and that should come to about 49.3. And if you look at the picture, we're off by decimals here because we're measuring, we can't get everything, but if you look at it, it's about 50%. I'm gonna look at it from here to here. It's about the same distance from here to here. So that's close to 50%. That means of all the solar radiation that's coming into the Earth, 50% of it is taken in by taken in by the Earth's surface. So that's pretty intense sunlight. That's where most of the heat's going to be, and that could explain why the equator gets so much more heat than elsewhere. Now, if we look at the other ones, so this was about 50% right here, you can see that this is going to be less. So you're going to measure from this point to this point. Oops, sorry, off screen. So from point A to point B, that's going to be about 50% of that radiation. And if we go from point B to point C, we're going to see that that's a little bit less. We're going to measure how many millimeters that is, and we're going to multiply that by what our conversion ratio was. And then from point C to point D, that's even less. Now understand that this is all 100% of the sun. Look how much less it's getting up there in the Canadian area versus the area that's Mexico. It's a lot more intense. They're getting a lot more sunlight, intense sunlight, than they are getting in the northern latitudes. And that's what we're trying to get at. So that's how you guys do number 8. Question number 9, use the protractor to measure the angle. So once again, you guys are going to use this protractor to measure what the angle is at each one of these points. Now this part's a little bit complicated, and I hope I can show you guys how to do this really well on your screen. Once again, I'm going to try to make this picture a little bit bigger for you guys to work with. But at the equator, the surface of the Earth is, if we draw a line tangent to the surface of the Earth, we're going to do that. We're going to line up our protractor like that. And what angle, so you want to like have this go out even further. So there's the sun right there. What angle is it hitting on the surface of the Earth? Well, at 0 degrees equator, that angle is 90 degrees. Okay. However, here at 30 degrees, you're going to draw a nice big long line like that. So that's the line tangent to the Earth. And notice that the sun is not directly overhead here. The sun is hitting this at an angle. So when I measure this, notice that it's only at about 60 degrees. So the sun's hitting the Earth at a 60-degree angle. So if you're at the equator, the sun's hitting you at a 90-degree angle. Here it's hitting at a 60-degree angle. You're going to do the same thing here. And let's just look at the North Pole. At the North Pole, the Earth is perfectly flat right there, and the sun is coming in like this. So it's actually hitting the North Pole at a 0-degree angle. That means that the sun is directly above. The sun is directly on the horizon. You can't look up at all. The sun's never directly ahead on top of you, down at the equator. Okay. Let's see. So that goes through and answers questions number 9. And then I want you guys to start figuring out what's the general relationship between the amount of radiation that you get, the intensity of the radiation for each 30-degree segment. So this is 30 degrees, this is 30 degrees, this is 30 degrees of latitude. What's the intensity like? And in your own words, question number 11, explain in your own words what facts about the Earth creates an unequal distribution of solar energy. In other words, solar energy, what I'm talking about is why is there's more solar energy taken in at these latitudes than these latitudes? And that's what I'm looking for, question number 11. So that's it for part 2. I'm going to move on to making a video for part 3 as soon as possible.